Welcome to our second Geometry Week. I'm hoping that you enjoyed the chance to create the geometry PowerPoint. I realize that you're not likely to find geometric perfection, but then again, remember, we're dealing with Van Healy level 0 and 1. So if you can honestly look at what you found out and said that this is a plane because it looks like a plane, that's going to meet the goal of the assignment perfectly. The goal here, again, remember, is to try and find examples to help generate this working vocabulary for students. And in particular, level 0 and level 1 students, that we want to get them to recognize the features just based on visual appearances. And that's as far as we're going. I always look forward to seeing the examples you come up with, and I'm sure this year will be no different. It amazes me the creativity that people are able to come up with. So again, I hope you enjoyed it. I hope you had a chance to get out a little bit and take a few pictures if you already didn't have them all. I hope you were able to have some good times with it. And if not, I hope at least you're able to learn something. A lot of those words were rather different, weren't they? They were including some that you might not be as familiar with. One of the things that you probably noticed in working through the geometry PowerPoint was that it's difficult sometimes to show a three-dimensional figure in a two-dimensional space. And so in order to kind of give you an idea of why this skill is important, as well as some ideas on how you might proceed, I'm going to share this little video that I prepared with you right now in terms of visualizing two dimensions and three dimensions, and also how you go about sketching, because it's through the sketch that we create a record of action. This turns out to be extremely important because when we're dealing with geometry, the object itself is the object that we're acting on. And so as we work with that object, we have to be able to create a sketch of it. So for example, if we take a look at this figure right here, you notice that it has three dimensions, but it'd be rather difficult to draw an accurate sketch, isn't it? And so this ability to sketch three-dimensional objects is important. And hopefully the video will show you why, as well as giving you some ideas on some things to consider and some things to include.
In this video, we're going to take a look at some of the properties of two-dimensional and three-dimensional shapes with the goal of reinforcing for you just how important it is that young people have the opportunity to personally experience the shapes themselves and not just rely upon a picture. As I've arranged these here, you'll notice that everything in this column, if we look at it just in terms of two dimensions, could be confused for looking circular, just as everything in this column could be confused with looking rectangular, and in fact the top two almost look like they could be squares. This is a common problem with young people when they see a picture in a textbook of something that they haven't had actual physical experience with, because once you've experienced this in the full three-dimensionality, not just as a picture in the textbook, we get a totally different perspective. So you see what we have here is we have something that, yes, does look circular in cross-section, but is actually a cylinder, like a can. And so if I had not had personal experience with what that object might look like, it would be very easy for me when seeing it in a textbook to confuse it for a circle. Just like the same here. This looks very circular when I look at it, but when I pick it up and I start experiencing it in three dimensions, I realize what I have is a sphere. And so even though it might look like a circle in the textbook when it's flat on a two-dimensional picture, when we experience it in the third dimension, we realize that it's not as simple as just a circle, it's actually a sphere. Take a look at this one. Again, it looks very much like a circle. And yet, when we look at it in three dimensions, what we see is we see that it's a cone. And in this case, it's a circular cone, isn't it? And so we see a much different picture if we've had actual experience with it in 3 dimensions as opposed to just seeing these 2-dimensional representations. Up here, for example, even though this one looks like a square, and I'm trying to get my sphere so it stays put here, I may have to move it. Yeah, I'm just going to move it off. Even though this looks like a square, when we lift it up and we start exploring it, we recognize that, oh my, it's a 6-sided figure. Each side is a square, and so you could call this a cube based on our experience with other 3-dimensional figures. This would be a cube. What do we have here? Well, it looks like a square if we just see the 2-dimensional piece of it, but when we start looking at it in the full 3 dimensions, what we see is that it's a pyramid. It has a square base, and then it has triangular faces. So this would be a square triangular pyramid. Finally, for completeness sake, even though this looks like it's just a rectangle, when we experience it in 3 dimensions, we realize that it's a rectangular prism, that it has dimensions of height, width, and depth that we have to account for if we're going to fully understand what that shape is all about. And so, in closing here, we have to be very, very careful, especially with young people, that we don't just limit ourselves to the 2-dimensional pictures. These pictures are extremely easy for young people to misunderstand, and we have to supplement that by giving them hands-on experience with the actual solids themselves, so that we can see and feel and gauge each of the 3 dimensions that goes into making up each of these very, very important geometric shapes. So let's continue this just a moment. Assuming the students now have experience with not only the textbook 2-dimensional picture, but also the 3-dimensional aspects of each of these figures, one of our jobs is going to be how do we create a representation of what the students have seen to help them recognize it. Clearly, if we just draw a picture like this, we're going to be hard-pressed to see if it's a cylinder, if it's a circle, or if it's a cone. And so when we draw something like this, one of the things you want to do is you want to make sure that it captures the essence of the figure as best you can in 2 dimensions. And so in this case, we see we have a circular base, and we see that it comes up to a top like this, and so that might be a better sketch for what we have going on here, that it looks a little bit more like a cone than if we were to just draw a circle, or alternatively, if we were to just draw a triangle. And so this would be preferred as our representation. There's no way that this would carry enough information, and this would not carry enough information. But where this has features that include all 3 of the dimensions, I hope you can see how that actually gives us a better picture for students to work with in terms of how to draw a sketch of what that might look like. Since we're dealing with 3-dimensional figures, it's important that we try to find some way of showing each of the 3 dimensions. That's why we tried to show the circular base and the triangular cross-section for the cone. So as we look at the cube, this is not necessarily the best sketch. If we were to just draw that sketch, it would look like a square. What we'd like to have is we'd like to have something that captures all 3 dimensions of the cube, and in particular so that we could label them, so that we would know that this distance is equal to 1, that this distance would be equal to 1, and that this distance would be equal to 1. You notice now that what we're doing is we're taking a specific way of putting that cube so that we can see all 3 of those dimensions. And whenever possible, we'd like to be able to label those dimensions, because that becomes part of the record of action that we're referring to. Now, because the object that we're acting on is the geometric shape itself, The record of action of anything has to include the sketching of that action. So if I take a look at what this might be like, you notice that we wouldn't just draw the square, that's the base of the pyramid, but somehow we would have to show the triangular features of the pyramid as well. So perhaps we show something that shows the square base of the pyramid, and maybe we draw some dotted lines here to show the internal of the pyramid as well. With practice, you can get where you can represent each of these figures, but it does take practice. For example, in looking at the cylinder, what are the key features of the cylinder we have to preserve? Well, first, it has a circular cross-section, and second, it has a height. So as we draw our sketch, we have to make sure that in some fashion we show the circular cross-section and that we show the height. And so again, in an ideal world, we'd want to be able to label the key features. So we'd probably label the radius, and then we would also label what this height is as well. This way, the record that we're creating from a sketch perspective can preserve the three-dimensional aspect of the figure itself while still being able to put in 2 dimensions as we draw this out onto a flat sheet. So here again we have a rectangular prism. We want to preserve all 3 of the dimensions, and so it looks like we have something like this. What you will find is that it's not immediately obvious sometimes how to draw these sketches, but with practice you can get better and better at it. And this is very important because when students think about these things, they have to have a way of recording their work that accurately reflects the three-dimensional aspect of the shape itself, but can be recorded in the 2 dimensions that they're going to see in terms of papers and textbooks and so on.
I am hoping that some of you were intrigued by fractals. Fractals are very new in terms of the curriculum. The key here is something that is self-similar at every level of magnification. And let me just share with you very quickly what this might look like when we start with an equilateral triangle. So let's take a look and see what I mean by self-similar at every level. When we think fractal, that really is the key feature, is something that is self-similar. So let's imagine that we start with an equilateral triangle. We'll have to do a little bit of let's pretend here because, you know, I'm just drawing this freehand. But if we can imagine this is an equilateral triangle, perhaps like the triangles you'll be seeing later in our discussions here, we need to know what an equilateral triangle looks like first, so we have a kind of a sense of what that is. Equilateral, that means equal sides, so we have 3 equal sides. We could call it equiangular because each of the angles would also be equal, but naming, of course, the naming convention is that it's equilateral, equal-sided. Now, imagine that I come in 1/3 of the way on each of these legs, and I paste another equilateral triangle on each side. All right. Now, of course, since we're thinking about a fractal, this is something that continues. So we're going to come in now and imagine that we are coming in 1/3 of the way on each side of this equilateral triangle, and we're going to paste yet another equilateral triangle. And of course, we can continue this and continue this and continue this process, can't we? And so if I were to take a magnifying glass and look, there's my magic magnifying glass, and look just at what I'm seeing right in here, what would it look like? Well, what it would look like is it would look like that I have a side with an equilateral triangle pasted on it, and then another equilateral triangle pasted on that side, and another equilateral triangle pasted there, and another one pasted there, and another one pasted here, and another one pasted here. And so now let's take our magnifying glass and let's look at what we have if we look at this. What would it look like? Well, it would look like a side with an equilateral triangle pasted on it, and an equilateral triangle pasted on that, and an equilateral triangle pasted on that. And I think you're going to start seeing the story here, aren't you? No matter how many times we zoom in on this, we're going to see something that looks the same. We're going to see a side and an equilateral triangle pasted on that, and another equilateral triangle, and so on and so on. And of course, it never stops mathematically, right? We can imagine this going on to infinity, even though my hand would get very tired if I had to draw that many. So in looking at this, you'll see what the fractal has kind of a family resemblance here. There are certain things that we can see about it, but it's easy to describe. In this case, it's built around an equilateral triangle. And as it's built around this equilateral triangle, what we see that it is built on larger and larger repetitions of this same basic pattern. And that's the beauty of fractals, is that they generate absolutely stellar, beautiful, beautiful patterns from relatively simple constructions. I'd like to make you aware of some of the resources that I've made available to you in Blackboard to give you the opportunity to explore fractals more fully. Based on past experience with my students, I have found that this is often an area of great interest, especially with young people as well. So let's take a look at a couple of things here that you now have access to. First of all, there's this absolutely lovely video, What is a Fractal and What Are They Good For? This is created by a group out of MIT, very nicely done. I think that you will find this is worth your time to watch as well. I'm going to give you that opportunity. It's not required, however, but I think you would find that it really does a nice job and gives you an excellent idea of some of the applications of fractals, and again, worth your time to watch. The second resource I'm making you available for is the Fractal software page. And if we click on this, it should open up a link for us to the Fractal Foundation. What's lovely about this is that there's some low to no cost whatsoever tools here. My favorite is Chaos for Windows. It may not be spelled the way you're used to thinking of chaos, but remember the Greek for chi. There's Chaos for Windows. If you have a Mac, you can run it on the Macintosh also. If you install that, what you will get is you'll get a program that opens up looking like this. And I'm going to make it full screen so we can see it. This is probably one of the more famous fractals out there. It's the Mandelbrot set. And to show you the difference that about 30 years has made, the first time I programmed a application to create a Mandelbrot set, it took about 3 hours to do one image like this. And now computing has gotten to the point where we can create dynamic panoramas on the fly. You'll notice I can zoom in, I can zoom out. There's a lot of options up in here, like I can pick which fractal formula that I'd like to take a look at. Each one, again, has its own features. Very, very fast. I'm going to encourage you to play with this a little bit. I think you'll find that the interest that fractals can generate, particularly when we realize how powerful it is, as outlined in the video from the MIT group, that we'll see that this really gives you a nice hands-on ability to explore fractals in a more dynamic sense. The object we're acting upon here is rather interesting, by the way, because it's living between sketch and abstraction. And there are some features of it that we can actually act upon, like I can zoom in, I can zoom out. It's almost like it's a physical object somehow, and yet it has the sketch features. a lot of the computers, a lot of the technology that we use in math have this ability to where to the learner, they feel like a physical object, although you're really interacting them at a sketch level. At any rate, I'm going to encourage you to explore that. I think you'll find that it's definitely worth your time, especially since it's a freebie. I like things that are low to no cost or free. The final video here that you can explore on your own is geometric fractals. What I like about this is that it shows you how these fractal patterns look like in nature. And so in looking at this, we can see that one of the more powerful notions in geometry now is fractals, because fractals explain a lot of the natural world that we see. And I had to show this one right here because this is the Sierpinski triangle. And later on in this discussion, you'll see Dr. Sack and I as we create basically this much of a Sierpinski triangle. The other thing that we'll be having you take a look at is 2 videos using these giant equilateral triangles. And since we can't use them hands-on in an online class, the first video that I'll share with you is a little description about what the triangles are and how we would typically use them. They're 1 meter on a side, so that gives you a sense for just how large these actually are.
Hello, I'm Jackie Sack. I'm an assistant professor at the University of Houston downtown in the Department of Urban Education, where I teach mathematics methods courses. Thanks. Thank you. And you.
That was cool. Y'all just so y'all can just take these and just stick them on top and keep making different shapes.
Yeah.
And I'm Michael Connell. I'm a professor in the same department. I also teach math education.
Using kite material. So these were manufactured by a kite manufacturer, and basically it's the seams over here are just black hollow seams that have hollow carbon rods down them, and then this is just a nylon thread that passes through the carbon rods and ties together, and that's what holds the triangles rigidly. So I have had a set of these triangles for over 10 years with lots of use, and they're still in perfect condition. The mini grant that we just received allowed us to purchase a second set, and we're ever grateful for that.
I would, being the recipient of the second set, I would like to express my gratitude also. The enhancement this adds to the methods courses is significant because it allows my students to experience the mathematics in a different way. As adults, very rarely do we have the chance of getting the aha that our young children have when they interact with hands-on materials. And this is such a unique manipulative material that they can construct some personally meaningful mathematics in a way that they probably haven't done since they were young children themselves.
The other plus about this, just from a general methods perspective, is that we're also trying to model highly interactive, collaborative activities. And this one particularly lends itself to that because no one can be the boss of the construction. They are extremely dependent on each other in order to complete the required activity. So it's a really good modeling experience for them in seeing how mathematics can be built.
There are literally thousands of activities that could have been done from the same starting point, but each of them would share the same family resemblance. We'd develop our vocabulary, we'd have actions, we'd build meaningful mathematics through our guide of the organization, and when we have a record of action, then that becomes a point we can come back to reestablish and formalize the mathematics. Well, you know, the question of why would a math educator want to use these, to me, kind of raises why wouldn't they?
How does this connect to those important CCRI standards? So for one thing, we are looking at figures and their properties, as you will see in the main presentation, looking at the properties of 3D figures in terms of their faces, vertices, and edges.
It also seems very natural to go into transformations and symmetry. As you'll see in the main presentation, symmetry is very important when it starts time to count the faces, the edges, the vertices.
And that is the connection to the other mathematical strands.
And so we're generating a 1, 3, 5, 7, 9 number sequence. Well, it's not obvious why. You have to interpret, you have to connect the different strands of mathematics to get to that.
And the representations are verbal,
Verbal,
they're oral,
graphical,
they're graphical,
physical,
they're tabular.
functional.
The classroom example that we're going to share with you is very typical for the type of thing that you might have experienced if we were to have been able to have worked with the hands-on triangles in class. It's a poor excuse for being able to do it, but it's the best we can do under these circumstances.
We use these in our pre-service mathematics methods courses with those who are going for elementary and middle grade certification, and higher if necessary, but that's most of our population. So many of our students come in with, you know, a class like this may have anything from almost no geometry to quite sophisticated geometry knowledge. Anything. But what we have found is these activities are extremely engaging for all levels, and no one feels uncomfortable or left out. So this is going to be a highly interactive session. We want a lot of you out of your seats to come and help. And we just want to demonstrate one of the activities that we do, assuming that people come in with any level or no level of geometric understanding, and how quickly we can take it up to a reasonably abstract level in one lesson. Okay, so the most important thing that you need to know, because you'll be interacting with these things, is that each edge of each triangle has 3 ties. Okay, so they're very easy to connect together, and the way you do it is just with shoelace, the way you tie shoelaces, no knots. Okay, so just the normal, you can go quite tight, they're not going to break, and then the loopy thing. Okay, if you make knots, we're going to be unpicking for a few hours, but with loopies, you just pull the string and they come apart. So it's quite important to match up 3 on each edge so they're nice and secure. Okay, so I guess just like in any physical system, it takes a bit of work to organize and put together a structure, and it takes very little work to take it down and disorganize it, the whole entropy effect, if you will. So the way I like to start with this, and it's not at all intimidating to any student, is to just set them up on the floor. And we're going to talk about where you can go from this, but we're taking a particular trajectory that is one of many, and we'll show you where else we could have gone. So my first question would be, if we put 2 of them together here, and I'm looking specifically at that point over there, if I keep adding triangles to the edges, how many will I need to completely fill the space around that point? So there is some response. Some will say 4, some will say 5, some will say 6, and that's not a problem. We can put them together and create a figure. Let's have a nice color here. Okay. So I think we're all quite comfortable with forming a nice regular hexagon. And again, for those who don't have the basic vocabulary, this is an opportunity to talk about what is it. It's a hexagon. What kind of hexagon is it? It's a regular hexagon. Well, what makes it regular? Making sure that that basic vocabulary that we haven't talked about yet is in place for all. And they have built it so they're comfortable. So regular hexagon, all the sides have to be congruent, all the angles have to be congruent. That comes from the participation. Okay, so for this trajectory, what I'd like to do is remove one of the triangles. And of course, we can talk about what kind of polygon we have now. but we're not going to go there right now. But what would happen if I now if I connected all of these and I now connect that, what happens? So we engage the mental imaging, which is a really important component of learning mathematics and doing mathematics. So what happens? If these are all connected and then we close the gap, what's going to happen?
It's going to rise in the third dimension.
It's going to rise into the third dimension. What will it look like? A pyramid. And what will its base look like? So it will have a pentagon for a base? Okay, so here's your charge. Someone can come and complete this one, but then I also want one where we take out a second triangle and we connect it. And what will happen if I take out 3 triangles and connect it? What will happen if I take out 4? So I need some help from my audience, if you will. A bunch of people. I need one group to come out and complete this one, another group to do the 4, another group to do the 3, and then we will look at those. Yeah, just get down on your hands and knees and start tying. Yep. Yeah. Okay, so it's not that hard. You just have to get down here and find the matching loops. This is going to be the 5. So let's first get these connected and then for this one we started with 6 and removed 1, right? This one we started with 6 and removed 2. This one started with 6 and removed 3, so leaving 3. And I've just asked them to connect 2. So removing 4 of them and leaving 2, we can't form if we connect them, that's all it is, right? So sometimes people need to have the experience of why can't we keep on going? So this is all we can do. We okay with that? So one of the things we could go to is, I wonder how much space they occupy. I'm thinking of volume ideas, just to put that out there. So one of the trajectories might be, how do you find the volume of a pyramid? So it's got to do with the product of the base area and the height, right? So here we have the largest base area. Here we have the smallest base area. But we have
I'm just sharing with you a couple of pictures here in no particular order from former students as they worked with the triangles. You'll notice that some of them have built an icosahedron. Some of them have built a stellated icosahedron, stellated meaning star-like. So gives you kind of, again, a chance to see what type of activities are possible with starting from a very simple shape, that of an equilateral triangle. In this video, you will notice that it's labeled as the second math event. And you're going to be making something very similar through folding a net and taping it together. So you might want to watch this so you could get kind of a sense of what it looks like in a large scale as well as the smaller scale that you'll be working with. Final video with the giant triangles is Dr. Sack and I building the Sierpinski triangle that we hinted at earlier. Again, this is a fractal. See if you can see why. Now that you've had a chance to see how they would work in a classroom if you have a set, I want you to realize you don't have to have a set like this to do the same type of activities in your own classroom. You could make a smaller set of triangles using marshmallows and toothpicks. I'm sure some of you have done that before. You can also cut straw and thread it with yarn and build equilateral triangles that way. Or you can go back to the paper cutting machines. I know there's a lot of the schools out there that will let you cut equilateral triangles. I've had students who've made a set out of cardboard. There's a lot of ways you can go. And the reason I'm saying this is part of your discussion assignment is for you to tell me how you could do these type of activities in a classroom that does not have a set of giant triangles. So now let's have a little talk about what our assignment for this week's going to be. There's a new discussion section, and what I'd like you to do is to post a brief discussion concerning how you could modify the activities you saw in the giant triangle videos for classrooms that do not have a set. The second part of the assignment is for you to download, print, and fold the nets for both the tetrahedron and the icosahedron. I have both of these inside the folder here, and you're to post a picture showing yourself and each of these solid figures. If you want, you can have one in one hand, you can have the other in the other hand. However you arrange it is up to you. I'm going to give you a choice in terms of what you would prefer to do. You can either explore the website on animated polyhedra, and you can then select, download, print, and fold the net for 2 of the polyhedra that you see. Then post a picture showing you and each of these solid figures. Or, if you'd rather do something that's a challenge, you can follow the directions for the origami activity and create a stellated icosahedron. Since this is a little bit more demanding, I am doubling the points possible for it. So this gives you an opportunity to build up a little bit of a buffer on your points for the class if you'd like. Let me kind of guide you a little bit here to where you can find some of these resources. The net for the tetrahedron can be found right here. You'll notice that we are in Module 3. We are in Week 9, Geometry Part 2. The net for the tetrahedron can be accessed just by clicking on it, and then you can print it off. And you'll notice that this is fairly easy in terms of how you can do it. The fold lines are marked for you. You have nice tabs for you to fold it together and so on. So the tetrahedron net should be relatively easy for you. The icosahedron net is a little more challenging. You'll notice that, first of all, there's a lot more triangles to be concerned with, isn't there? And you're not quite sure, apart from the fact that you're going to be folding on each of these lines, how it might be put together. So I'm going to share with you a couple pictures in terms of what icosahedrons might look like so that you can see how you might have an opportunity to guess based on what you see from those solids to go from this flat net to a three-dimensional solid. As you examine the teaks, there's two skills that we have to make sure we can do. One is to go from solid to net, and you might remember this from your own experience with the test, where you had to say which of these flat figures could be folded up into a cube. All right. The other is to go from net to solid. So from going from solid to net, or from 3 dimensions to 2, or from net to solid, 2 dimensions to 3. Again, that work on visualization in 2 and 3 dimensions should come back to be helpful for us. The animated polyhedra website can be found right here. And in many ways, this is one of my favorite websites. So I'm going to take the opportunity just to kind of guide you through some of its features. The first thing that you'll notice is that we have the name of the polyhedra up here. You might want to explore this a little bit so that you can see what some of the names are. I'd recommend that you go down to some of the earlier ones rather than the later ones, just to make it easier to see. The tetrahedron, for example, is one that you will have made by going from net to solid. We can turn the spinning off and on, and I can grab it by the corner and I can turn it around here and try and picture what it's like. I can change how the coloring looks. I can change whether I can see through it. I can change whether it is just the beams that I see or whether I see everything involved with it. A lot of options. What I find that works best for me is that when I find a tetrahedron that I like a cube, for example, I kind of explore it a little bit. I see what it looks like. And then I say, okay, what does the net for that look like? Well, I'll turn the solid off and I'll turn the net on. And if we look at this, we can see how we could cut this out and how we could fold it and make a cube. In fact, this could have came straight out of the STAR test, couldn't it? It almost looks like it. So your task is to find 2 of these figures that you like. And I would suggest that you look at it from the solid perspective first. And then once you find the 2 solids you like, get the net, print the net. See how I'm getting down here? Print the net and then create the solid. You're going to have to do that twice. You get to choose which 2 that you would like. And that would be your first option if you decide that this is what you would like to do as opposed to the origami. The origami is kind of an extra for experts, which is why I'm giving you double points for it. It does take time. I've had a number of students who've done this in the past, but they tend to be people who have liked origami already. So if you would like to do this, I would encourage you to try it. It links up to a really nice website. It just takes time more than anything. Once you learn how to make the first fold, then everything after that comes pretty quickly. You just have to fold a lot of these and then start tucking them together. I'm not going to say too much more about it because I don't want to steal the fun that you might have if you decide that that is the route that you'd like to go. But it is a challenge. I'm not going to lie to you. It is a challenge. So that's why I'm giving you an option here in terms of which way you'd like to go on that. So having said that, that gives you the overview for what the week will look like. I will come back with you again here about our asynchronous assignment for next week. But this is what we will be doing for the remainder of today and for the first half of your asynchronous assignment for next week.